similar to a problem that I'm sure you will have on your test. You will have one like this that'll have multiple parts. I don't know exactly what the parts will be. I don't know whether it'll be an inductor or a capacitor, but you're going to have something where you're going to have, it'll be worth a good amount of points, but something kind of like this. And so here you have a circuit, and it says the switch has been in position 2 for a long time, and then moved to position 1 at time t equals 0. And we are supposed to find some various different things. So one thing you have to be able to do is to draw what the circuit looks like at the different time periods, and how the different elements are acting at those time periods. So before t equals 0, it says it was in position 2 for a long time. So if it's in position 2, then I think this one says but this one we're starting in position 2. It's just a different problem. So they used the same circuit for 2 problems. We did position 1 the first time. So this is problem 2.
Sorry.
Yeah, that's okay. So it's in position 2. And so that means that resistor R2 is not connected to anything. And it means that our capacitor, I'm going to draw it as an open circuit because if it's been sitting under DC conditions for a long time, it'll be an open circuit. You can also draw it as like an instantaneous battery if you want to do that. And R1 we know is 30 kiloohms, and R3 we know is 60 kiloohms, and our voltage is 12 volts, and our capacitor has capacitance 100 microfarads. All right, so let's find out everything we can about this capacitor at time before time t equals 0. So before t equals 0, the current is easy. It has to be 0 amps because it's acting as an open circuit. And so that has to be 0 amps. Now that current can change instantaneously. Whatever its voltage is right before t equals 0, it has to be the same right after t equals 0. And the way you find out what voltage a capacitor has is by finding something it's in parallel with. It's real tempting. When I first started to do this, I thought, well, current's 0, voltage is 0, but that's not true. So the voltage is something it's in parallel with. Now, is it in parallel with the 60 kiloohm resistor?
Yes.
Yes. Is it in parallel with the voltage source? No. The reason it's not in parallel with the voltage source is because of the 30 kiloohm resistor. So it can't be in parallel with the voltage source. So the voltage source is not in parallel with anything because of that 30 kiloohm resistor. But it is in parallel with the 60 kiloohm resistor. And so I know, I can look at this and say, well, I know that the voltage change across this 30 kiloohm resistor has to be 4 volts. And the voltage change across the 60 kiloohm resistor has to be 8 volts. But that's because I've been doing this a while, but the way I did it is, and I'm going to show you how to do it without just looking at it and saying and knowing, but the way I did it is I saw the 60 kiloohms is twice the 30 kiloohms. And so the voltage change across it has to be twice the voltage change across 30. And the two of these have to add together to give 12. And so I've done this enough times that I say, oh, I know what those numbers are. They're 8 and 4. But you're not expected to be able to do that. But what you are expected to be able to do is voltage division. And so to find the voltage across the 60 kilo ohm resistor, you take the total voltage change across both resistors, which is 12, times the resistance of your resistor, which is 60 kilo ohms, times the resistance of both resistors in series, which is 90 kilo ohms. And unless I'm mistaken, that is 8 volts. And the plus is on top and the minus is on bottom because it's going to match with this voltage source. It's the plus, the higher voltage is going to be on top. So that tells me, since the capacitor is in parallel with this resistor, I know the voltage of the capacitor for t less than 0, right less than 0, has to be 8 volts. But that means that I also know that the voltage on the capacitor at t equals 0 has to be 8 volts because it can't change instantaneously. Okay, are there any questions on that so far? All right, so now let's look what happens when we flip the switch, because now we'll have, things are going to change. We're going to go to position 1. So when we go to position 1, R2 is 120. R2 is 120. R3 is 60. Okay, so when the switch gets turned to position 1, right here, then all of this becomes part of an open circuit, and it's not going to play any role. So that's all open, it's not connected to anything, and so we only have to look at the other part. Okay, and our current we have that we're supposed to find is right here. So this is at t equals 0. So at t equals 0, we have this set up. The only thing we can mark when we start is this 8 volts. We know we have to have that 8 volts. We don't know anything else at this point because the currents can all change. Now, are these 3 elements in parallel? Yes. So I know that they all have the same voltage. If I make this ground, then I know I've got 0 here and 8 volts up here. Now, the way you find the current through a resistor, if I have a resistor and I have a voltage here of VA and a voltage here of VB, and I'm trying to find the current going in that direction, that current is VA minus VB over R, and that's just Ohm's law. So if I want to find the current through the 100 kilo ohm resistor, call that I1, this is I2, and IC was given in the problem. So I know I1 has to be 8 minus 0 over 120K, and I2 has to be 8 minus 0 over 60K. So I'm going to divide 8 by 120, and because I'm dividing by 120K, I know that's going to give me milliamps. So rather than dividing by 120,000, I just am going to say I know my answer is going to be in milliamps. Okay, so I get 0.066, so 66.7, or no, I guess that's already in milliamps. Yeah, 0.0667 milliamps. And then 8 divided by 60K will be twice that. Will be 0.133 milliamps. So I have 0.0667 coming down here, and I have 0.133 coming here. So what does that mean has to be happening right here? So KCl basically says current in has to equal current out. And this bottom branch right here, this is a node. So a node, it's all connected by conductor. There's so this is all one node. It's all connected. So any current coming in has to be the same as the current going out.
So IC would be I1 plus I2, the negative?
That's right. Yep. So this current, the current going up is going to be 0.0667 plus 0.133. Which is 0.2, but that is going up, and so IC, and that's milliamps, IC is going the other direction, so IC has to be negative. So IC is 0.2 milliamps. This is at T equals 0. Now, this is the kind of problem that you like to see when you get to the part with T at infinity, because when I look at T at infinity, when I look at T at infinity, it's the same circuit as T at 0, just it's been going on for longer. And when I look at this particular circuit, I notice it has no sources. There's no current source, there's no voltage source. And so when we started, our capacitor was going to charge, was charged. As the current flows, every time the current flows through a resistor, the resistor absorbs power. It's absorbing energy. And so the energy that was stored in the capacitor gets dissipated by the resistors in the form of heat. So all of the energy the capacitor had, which by the way, the energy that it had was 1/2 CV squared. It was 1/2 times 100 times 10 to the minus 6 times 8 squared. So you could figure out what that was. That is something you need to know how to do. So that's joules. So that was the energy it had. All of that energy gets dissipated by the resistors. So a question that you could ask about this would be, from the beginning, like just a question, how much energy gets dissipated by the resistors as time goes to infinity? And the answer would be whatever this number is. So when we get to infinity, there's no more sources, so there's no source of energy, and so there's no more voltage, and there is no more current. So at t equals infinity, VC at infinity is 0, and IC at infinity is 0. So that's nice. Okay, so then, let's see, what do the questions ask? 0, infinity, and then we want VC of t and IC of t. And I don't know why I have an extra C on part C. I didn't really want CIC, just wanted IC. Okay, so now if you look at what I'm going to give you this evening, the first page of that has all the good formulas you might possibly need. And so what we would need for an RC circuit, which we have right here, is this one. So that worksheet is in SI Resources, and I'll have some of them printed out tonight. Just a few, not enough for everybody, but okay. So this is the equation that you use for an RC circuit. So the last thing that we need to find is tau. So tau is RC, and R is the Thevenin equivalent resistance as seen by the capacitor. And you look at the circuit the way it is between 0 and infinity, which is this circuit right here. So we had 120K and 60K. This one's nice. It's not too tricky. There's nothing. It is what it looks like. So from the point of view of the capacitor, are those resistors in series or parallel? Yeah, they're in parallel. So our equivalent will equal 60K times 120K over 60K plus 120K. The nice thing about those Ks is you'll notice if you, on top, they multiply together to give K squared. On the bottom you would add and you'd have K, and so 1K would cancel out, so you'll just end up with K in your answer. So you can kind of just ignore the Ks when you do this and know that your answer will be in kiloohms. So, that was funny. Okay, so 7200 over 180 kiloohms, which is 40 kiloohms? 40 kiloohms? Did anybody just verify that? Okay, so our equivalent is 40 kiloohms. C was given to be 100 microfarads. So RC is 100 times 10 to the minus 6 times 40. So that is 4 times 10 to the negative 3. Or 4 over 1,000.
So RC is like the total resistance in the whole circuit, and then the total capacitance in the whole circuit.
It's so let's say it's the capacitor that you're looking at.
Yeah.
Yeah, because you could have a circuit with more than one capacitor. So we're dealing with this capacitor, so it's its capacitance, and then the all the resistors that it sees. Now, I like to actually think of my formula a little bit different than the way it's written, just because it ends up with something nicer. So I have v at time t equals v at infinity plus v at 0 minus v at infinity times e to the minus t times 1 over tau. So what I always do is I just get 1 over tau instead of tau. So tau was 4 over 1,000, so 1 over tau is 1,000 over 4, which is 250. So then my v of t is 0 plus 8 minus 0 e to the minus 250 t, and my answer is going to be in volts. And so that is just v of t is 8e to the minus 250t volts. I always wait until like now to check my solutions to see if I have the right answer. And I forgot something? Did I forget something?
I got 4,000 times 10 to the negative 3.
4,000 times 10 to the negative 3.
RC for C.
Did I get my RC wrong?
Isn't R and kilometers? Not just.
Yeah, it is. Yep. That is where I messed up. So this would be K.
That would just be 4.
Well, it would help if I was looking at the right problem. I don't even have the solutions to this one. Yeah, so it'd be 4. So this would have been times 10 to the third. So that would be 4. So this would be 1 over 4, which would be 0.25. So 0.25. Let me check. Let me just make sure that's right. 2120, right? That's position 1, position 2. Tau is 4. Is that what we got 4?
Yeah.
Okay. Okay, so now our next job is to find I of t, and so to do this, you can go back and look at the formulas I'm going to give you, and you'll see that I of t equals c dv dt. So all we have to do now is take C, which was 100 times 10 to to the negative 6 farads, and then take the derivative of the voltage. So the derivative of the voltage will be negative 0.25 times 8 e to the negative 0.25 t. So negative 0.25 times 8 is negative 2. So this is negative 200 times 10 to the minus 6 e to the negative 0.25 t amps, or negative 200 times 10 to the minus 3 e to the minus 0.25 t milliamps, or negative 0.2 e to the negative 0.25 t milliamps. Now, all of that was just to make it look neater. I mean, the correct answer, any of those is the correct answer. They're all correct. I like this one because it's concise. Okay, so any questions on that before I stop this one and record and go on to the next one?